c'est lourd de pouvoir en parler.
So, honorable assistants, I have the honor to present you my work titled Electromagnetic and Thermal Behavior of an Integrated Octagonal Planar Microtransformer. So, in this work, we are going to talk about microtransformer topology and modeling. Then we will observe the different effects created at high frequencies. We know that power electronics has never ceased to evolve. Purely this discipline and in the electronics sector. Yes.
Sorry to interrupt you, on ne voit pas l'enchaînement des slides en fait, on voit juste le
il y a un retard, je ne comprends pas.
On voit.
C'est comme ça.
Oui, c'est ça.
Je ne comprends pas le déphasage qui est là.
Peut-être vous pouvez sortir du mode diaporama et en fait passer par une des slides si ça peut marcher. Voilà, c'est bon.
Okay. So, honorable assistants, I have the honor to present you my work titled Electromagnetic and Thermal Behavior of an Integrated Octagonal Planar Microtransformer. In this group, we must observe the different effects created at high frequencies. We know that power electronics has never ceased to evolve. Currently, this discipline is present in the majority of electrical systems. We know that power electronics, in the electronic circuits, passive components occupy 80% of the area. In the circuits, the integration of active components has now become a classical thing. However, only the integration of passive components remains the obstacle of miniaturization. Therefore, the transformer is considered a coupling between two inductors. Objective of this work is to integrate the transformer with the planar octagonal network of coils at high frequencies. In this work, the microtransformer is composed of two sphere planar coils with octagonal form. The primary coil has 3 turns and the secondary 2 turns. The coils are stacked on magnetic layers of ferrite and dielectric layers of silicon dioxide. The following equivalent electrical circuit describes the electrical behavior of the microtransformer. We notice that at high frequencies, there is a creation of capacitive effects in coils.
Qu'on a utilisé pour notre simulation. Donc on voit bien le rouge qui représente la densité, la conductivité thermique, ainsi que la chaleur capacitive. Sur le premier graphe, en utilisant un mètre de 1 mm pour notre décharge partielle et en comparant.
For the sizing of the magnetic circuits, we evaluate the volume of the magnetic core in ferrite material, which allows us to describe or to define the section on which will be placed the spiral coils And we have opted for the core area of 1,500 by 1,500 micrometers squared. The volume is calculated from the stored energy and the energy density. So we have found 0.122 millimeter cube of NEZN field. The size of the electrical circuit, the coils are planar spiral with octagonal form. To calculate the inductance value, we don't use the standard formula of inductance. But for the microscopic scale, we use another method. In this work, we have opted for the Wheeler method because it is easy to implement and it gives good results and it has a low error compared to the other methods and allows us to and this method allows or remains valid for reduced number of terms. The different geometrical parameters values are included in this table, and we notice that the results are consistent with the integration in electronics. The following step is the electrical dimension, which we transform the stack of different layers to the equivalent electrical circuit. Every layer is represented by electrical parameters, which are represented by those expressions. For the serial resistance of conductor coils, the current passes through the skin thickness. It means the peripheral of the conductor and not the global area of the conductor coil. The different electrical parameters calculated are represented in this table. And the stack of different layers of different materials allows to create a different phenomenon. We define E1 the electric field between coils due to the coupling capacity, due to the ohmic losses, and E2 is the electrical field between the coils due to the coupling capacity. E3 is the electric field between the spiral coils and the substrate due to the oxide and substrate capacities. B is the magnetic field due to the direct current circulating in the spiral coils. Based on the Maxwell equations, which link the electrical phenomenon to the magnetic phenomenon, we show the distribution of magnetic field lines in the microtransformer. We notice that the magnetic field lines are distributed in all directions, and that allows to disturb the closed components in the same circuit. However, when we add the magnetic layer in field, it allows to confine all the magnetic field lines, and that is due to the high permeability of the field in NEZN material. The heat transformer is done by heat conduction and heat radiation. The coils of the microtransformer are considered as the heat source which comes from the Joule or ohmic losses. Using the green equation, we show the distribution of the temperature in the microtransformer. We notice that the temperature value achieves 110 degrees Celsius in the microtransformer in the air. However, the temperature decreases to 75 degrees Celsius with the addition of the magnetic core in field. And this is due to the high permeability of this material. The conclusion can say that this work is part of the integration problem of passive components, and our objective in this work is to reduce the size of the microtransformer. And our study is about electromagnetic and thermal behavior created in the microtransformer. So the integrated microtransformer is composed of two octagonal planar spiral stacked coils. We have used the finite element method with a console tool, And we have demonstrated that the addition of the magnetic core in field in the microtransformer serves to confine the magnetic field lines and to decrease the temperature to avoid to starve the closed components because of the high permeability of this field material. All the results that we have qualified in this work are compatible with the integration of passive components. And for the prospect, we plan to integrate the transformer with the other passive components like the inductor and the capacitor to create a new passive component with reduced dimension named LCT in order to make the microconverter, which is our aim, to make the microconverter completely integrated and stand alone. Thank you for your attention.
Ok, merci Mokhtaria pour la présentation. Donc, the floor is open if there is any question. S'il y a des questions, s'il vous plaît, on a le temps pour prendre une ou deux questions. Donc, comme la présentation est en anglais, permettez-moi de poser une question en anglais. Donc, which software have you used, Mokhtaria, for your study?
In our study, we have used the console 5.3.
Okay. As per what I have understood from your presentation, you have used the electrical design separately from the mechanical design or the design itself.
The electrical design of the microtransformer, every layer become represented by a small circuit. It means when you put the coil in the conductor, this coil will be represented by the inductor in series with the resistance, the serial resistance, and these two components in parallel with the capacitor in high frequencies. For example, for the other layers, like field, it is represented by only the resistance, and for the dielectric layer is represented by the capacitor, and for the substrate, which have to regroup all the stack layers, it is represented by the dielectric and serial resistance.
Okay, you have used 3D FEM.